Hello everyone, I'm Paul and today we're solving problem 808, soup servings. This is medium but tricky honestly, and next I will show you how to solve this efficiently. We have two soups, A and B, and we are given only an integer n, which represents the milliliters for each of these soups. In any turn we can see any of these four operations, each with a probability of 0.25. And our job is here. We need to return the probability that A is empty before B plus half the probability that both soups are empty in the same turn. And this is important. If an operation asks you to pour more than what you have left of one soup, pour all that remains of that soup. So I will show you what's the overall approach to solve this, and then I will show you why I think this is a hard medium. Let's say n is 50. This means that A is initially 50 and B is also 50 initially. Now from here we have four possibilities. This is the first scenario. Here we pour 100 milliliters from A and 0 from B. So the remaining milliliters are minus 50 for A and 50 for B. And these are these three scenarios. For example, here we pour 75 milliliters from A and 25 from B. These are the remaining milliliters. Here we pour 50 from A and 50 from B, so remaining is 0 and 0. And here we pour 25 from A and 75 from B, so we get A equals 25, B equals minus 25. Now we need to return the probability that A is empty before B plus have the probability that both soups are empty in the same turn. Now as you can see, this looks a lot like a tree, and of course this tree could be larger. If A and B are both greater than 0, well, we would continue with 4 more operations. And whenever we are carrying a state with us and we have a tree, and at each step we are transforming the state, we are keeping track of the previous state and we are using that to get a new state, meaning we are keeping track of previous results to get new results. This looks a lot like dynamic programming. So we will have different base cases here. First, if A is smaller or equal to 0, this means we can return 1. For example, here we can return 1, and here we can also return 1. Now if B is smaller or equal to 0, meaning soup B is empty before soup A, we can return 0. So for example here we return 0. Now before checking this, we can check if A is smaller or equal to 0 and B is smaller or equal to 0, we return half the probability that both soups are empty in the same turn. So 1 divided by 2 is 0.5. So for example here we return 0.5. So now we are receiving each of these values here in the root, and the probability for each of these four operations is 0.25. So first we receive this and we do 0.25 times 1, and this is 0.25. If we receive this, we get the same. If we receive 0.5, we do 0.25 times 0.5, and this is 0.125. And if we receive 0, we do 0.25 times 0, and this is 0. So the value we are returning here is the sum for all of this, which is 0.625. And given that this is the root of the tree, we return this. Now this is fine, this works, but our problem is the following. Here we have the constraints and we know that n is smaller or equal to 10 to the power of 9. And you will see in test cases that if you increase n, the result also increases. So for example, if this is 200, the result is greater. And if this is 500, for example, the result is even greater. So at some point we have some n for which the result is 1. And from that point, every value that's greater than that breakpoint is also 1. Now the question is, how can we find this breakpoint? And the answer is, you either need to know about probability theory, or you can try different values until you find the breakpoint. So this feels like cheating, honestly, but the problem expects you to either try different test cases until you find this breakpoint, which is what I did, or maybe you know about probability theory, but that's not my case. So I tried different test cases until I found the number, the breakpoint for which every value greater than that is 1. And that value is 5,000. So with this in mind, the first thing we can do is to check if n is greater than 5,000, we just return 1. And if it's smaller or equal to 5,000, we implement our DP approach. And this is why I think this is a hard medium problem, honestly. So overall time and space complexity for when n is smaller or equal to 5,000 is roughly big O of n squared. And when n is greater than 5,000, time and space complexity is big O of 1. So now with all of this in mind, let's go with the code and hopefully you will get the idea. First we say if n is greater than 5,000, we can return 1 right away. Else, we can build our DP function. This takes a and b as arguments, and we can have repeated states here. So we need to cache this, meaning we are storing results for every combination of a and b. Now, here we have our base cases. First, if both subs are empty in the same term, meaning if a is smaller or equal to 0 and b is smaller or equal to 0, we just return half the probability that these are empty in the same term, so we return 0.5. Now, if a is empty before b, if a is smaller or equal to 0, we return 1, and if b is empty before a, we just return 0. Now the result is initially 0, and we need to add every possible scenario. Remember, we have 4 operations, and each operation has a probability of 0.25. So we do this times the first scenario, which is to pour 100 milliliters from A and 0 from B. So this is DP with A minus 100, and B stays as it is. For the next scenario, we say 0.25 times, and this is 75 milliliters from A and 25 from B, so A minus 75, B minus 25. Next, we have 50 from A and 50 from B, so this is 0.25 times DP with A minus 50, B minus 50. And finally we have 25 from A and 75 from B, so this is 0.25 times DP with A minus 25 and B minus 75. And finally we can return the result. So with this function now we can return a call to DP with n and n for A and B. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. This part is very tricky, honestly. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.